Welcome everyone. My name is Tomasz Pęczek. If you want to find me, reach me, I'm on Twitter. The handle is right there on the screen. And I'm here today to tell you a little bit about HTTP2. I could start with typical HTTP history introduction. I'm not going to do that. If you grab any book about HTTP, HTTP2, web applications performance, web application security, the mandatory HTTP history chapter is there. From history perspective, what you really need to know is that HTTP2 retains all the semantics of HTTP1. So all that knowledge, headers, methods, etc., it's still good, still useful. The first visible difference is that it requires HTTPS. And that's a result of choice of implementers. The standard doesn't actually require that. Browser vendors simply decided to allow it only in HTTPS to avoid infrastructure issues. That's a lesson learned from WebSockets. And that HTTPS requirement should actually not be an issue those days. The web is being pushed toward a secure context anyway, mostly due to privacy reasons. So, in context of this push, HTTP2 is just a reward, as many other functionalities which are available only in the secure context. And the value of that reward is improved performance. HTTP2 comes with promise of better latency, better network utilization by our web applications, better way that browser utilizes connections. And my talk simply aims at allowing you to get the best out of this promise and not hurt you, yourself, your users in the process. If you start learning about HTTP2, you will probably encounter two very popular statements. The first one is just enabling HTTP2 gives you a performance improvement. That's more true than it's not. But in early days of HTTP2, the Akamai Foundry team decided to conduct a study. The goal of that study was to measure how different browsers behave in context of HTTP2. What they accidentally measured along the way is that some URLs respond slower after switching to HTTP2. Now the study was not supposed to examine that, so there was no immediate conclusion out of this. After time, when the authors of the standards has told us more, we learned more, we know that in order to get that performance boost, you should orchestrate your entire page load. HTTP2 deals with the most important part of performance, the user-perceived performance. It is important for user to see that your page loads quickly. That might mean that some of the URLs that your page load is requesting will respond slower. That's not a bad thing, as long as the entire page load is faster. The second statement you will encounter is that optimizing for HTTP2 simply boils down to removing all the HTTP1 optimizations. Now, this is not entirely true. And this is potentially harmful. Let's take a look at can I use stats for HTTP2. They look nice. They are generally green, right? But that's a global view. This might not be your particular group of users. If you think about users from developing countries, they tend to use older browsers. They even tend to use older operating systems. Even in highly developed countries, think about organizations, companies. They are often internally bound to use a specific older version of a browser due to some legacy software they have. If you would take a tour around software as a service providers for HCM solutions, talent management solutions, talent acquisition solution, and you would ask them, do you still support IE, any version of IE? The answer most of the time would be yes. So those users cannot benefit from HTTP2. What that means is that if we simply remove the HTTP1 optimizations, all those users will be hurt. You don't want that. You want to be responsible. You want to get the best for both worlds. So in order to achieve that, in order to optimize properly for HTTP2 and not hurt the HTTP1 users, first I need to show you a little bit more about how HTTP2 works. The most important feature of HTTP2 is multiplexing. And it's about how HTTP2 uses the underlying TCP/IP connection. In HTTP1 world, it's simple. Every request, dedicated TCP/IP connection. It comes with a price. Establishing TCP/IP connection is expensive. It requires a couple round trips. The connection speeds up over time, the slow start problem. And maintaining multiple parallel connections is expensive from resources perspective. Browsers have hard limits of how many connections you have simultaneously opened to the same domain. This is the reason for that waterfall you see in the network tab of your favorite developer tools. First couple requests, they are relatively slower than the later ones. The later ones are waiting for the first one to finish, the head of line blocking problem. So HTTP2 with multiplexing aims at solving that. It simply states, there is only one connection. So we don't pay for establishing multiple connections. We don't pay in resources. The connection speeds up only once. Every request response becomes a logical stream. So your ultimate limit is the bandwidth. That's what HTTP2 attempts to do. Improve the latency by fully utilizing the bandwidth. In browser context, we usually have a lot of bandwidth, unless we are watching Netflix or YouTube in our free time. But other than that, we have bandwidth. So that's the solution for performance. It's nice. It's not perfect. There is an issue hiding in there. Those of you who know low-level network details a little bit better might know what that issue is. Packet loss. What happens to a TCP/IP connection when packet loss occurs? It stops. So all our request responses are simultaneously stopped. And what happens when the packet is transmitted? Because that's the reason of stopping the entire connection. It slows down. The underlying assumption is that the packet has been lost due to degraded network conditions. So it's better to start slower. Again, speed up over time. What that means for our applications? All our request responses are simultaneously throttled. So packet loss is a potential killer for HTTP2. And actually, Twilio decided to measure that. They have built an artificial network and introduced a constant level of packet loss to that network. As you can see, HTTP2, the red one, is really misbehaving when there's a lot of packet loss in the system. HTTP1 is a lot more resilient to packet loss. Okay, this is lab, right? This is not real life. Or is it? We are just after vacation period, right? You might have visited some remote area, I don't know, mountains, seashore, and you wanted to check your email. You wanted to publish that great photo on your Twitter feed. And you probably were doing some kind of get the connection yoga, yeah, like this. We don't always have great connectivity. There are whole parts of world where good connection is a luxury. What does it mean for us as developers? Should we enable, disable HTTP based on location? Well, that's probably too extreme, maybe as some kind of last resort solution. But we might think a moment if only a single solution is our best option. Maybe we want two connections, one for smaller critical resources. Eventual packet loss will impact there in a lesser way. The other for the big resources. In case of a problem, we can wait for them. The second very important feature of HTTP2 is Hpack. And Hpack is a feature that when you learn about it, you are surprised it haven't come earlier. It's about compressing headers. If you look at the headers from the global perspective, like let's say HTTP archive, they are extremely repetitive. over and over the same data are being sent over the wire. And that's the assumption that Hpack is using. It contains a dictionary, 2 dictionaries to be exact. The first one is a static dictionary. It contains 2 things. A well-known headers with well-known values. If such a well-known header with well-known value is in your request response, it gets encoded to a single byte. Identifier from the static dictionary. If only well-known header name is in your request response, that name gets encoded to the single byte, the value gets Huffman encoded. That's a simple compression algorithm. And the unlucky headers which are not there in static dictionary, they are entirely Huffman encoded. And that's not all of it. That's actually when the fun part begins. All this stuff that has been Huffman encoded ends up in the dynamic dictionary. So if any of those values reappear for the same TCP/IP connection, they get encoded to a single or 2 bytes. So in the end, all of this, those cookies, this user agent string, this can become 1 or 2 bytes. Now that's nice compression ratio. Not many compression algorithms can do that. Of course there's an issue there. It's not perfect. The problem is the dynamic dictionary. Actually, in early days of HTTP2, the dynamic dictionary was a source of first security issue for HTTP2. It was based on the fact how servers decompress the data. The attack was very simple. An attacker would open a single request, so established connection, with a very large header value. That header value gets Huffman encoded, it's added to a dynamic dictionary, then the attacker opens dozens of requests referencing the same header value thousands of times. As you can guess, that leads to using all the memory on the server, denial of service. That's no longer the problem. The server-side implementations are now resilient to this. But dynamic dictionary is still the reason why you can get the Hpack wrong. If you have a frequently changing header, that header constantly needs to be Huffman encoded. So that wasted CPU time. And the dynamic dictionary, for obvious reasons, is limited in size. So adding constantly new values at some point will cause evictions from dynamic dictionary. So those values which are there all the time, which are probably in every request, they will start disappearing. They will also need to be Huffman encoded again. The worst case of this issue is when you have a frequently changing cookie. Developers tend to forget how cookies look on the wire. In server side, it's simple, key value, right? On the wire, it's a very long string, potentially. So if you have a frequently changing cookie, even a small one, it means that this entire string needs to be constantly Huffman encoded, constantly added to dynamic dictionary. In the end, the Hpack might be burning enough resources to make the entire operation slower than it would be with HTTP1. So if you are using HTTP2, be mindful how you deal with headers, be mindful how you deal with cookies. And understanding multiplexing and Hpack is enough to challenge those HTTP1 optimizations. Let's look at the most well-known ones. I'll start with spriting. So a simple technique of putting multiple images together in order to send them at once, avoid head-of-line blocking. That's the goal. At first look, it sounds like multiplexing should solve that, right? Downloading multiple resources without head-of-line blocking. So should we remove spriting in HTTP2? Well, there is one potential problem. The images you put into your sprites are usually very, very small. So if you start downloading hundreds of them, thousands of them, the additional cost becomes noticeable. Every request, every response have some additional cost, even with Hpack in place. So it's better to still sprite something. You just need to think about it differently. Create a well-thought spriting strategy when you sprite together images that represent logically bounded areas of your application. One sprite for the menu, one sprite for the navigation bar. This way, you are still utilizing multiplexing, you're still opening multiple requests, download in parallel, utilize bandwidth. You avoid the extra price of additional requests. So you minimize that overhead that request introduces. There is also added value here. If your sprites are logically bounded, they have single reason to change. You utilize client-side caching better. If an icon in your menu changes, you will only invalidate the sprite responsible for the menu. That's a lot better from browser perspective. Bundling. So like spriting for CSS and JavaScript, or spriting is bundling for images. Regardless how you want to look at it, the rule is the same. In HTTP2, bundling is no place to put your third-party dependencies, your big libraries, Angular, Vue, Bootstrap, whatever the JavaScript framework of the hour is. That shouldn't be bundled. What you want to bundle is your small modules. If you are doing Babel and probably some module loader in your client-side code, then you tend to have a lot of very small modules, just a couple lines of code. And you usually minimize that. So those who are logically bounded together should be bundles, but not too big bundles. So your strategy needs to be well thought. Sharding. A very smart optimization technique. And I mean a software development kind of smart. So essentially a hack. It allows us to work around that browser connections limit by using either subdomains or different domains to download more resources in parallel. So that's exactly what multiplexing is trying to solve, right? So sharding in context of HTTP2 is bad. We need to deal somehow with that. If you would read about sharding and HTTP2, you may find information that there is not so well-known HTTP2 feature called connection coalescing, which will solve the sharding for you. The idea of the feature is like this. If two domains resolve to the same IP address and they are valid under the same certificate, HTTP2 should use the same connection. Sounds great, doesn't work. It's simply not consistently implemented in all the browsers. Take it from my experience, at least for now, you cannot rely on that feature. It will fail you at the least expected moment, it will cost you bandwidth, it will cost you money. So in HTTP2, simply remove sharding. What about some special cases of sharding? For example, cookieless domain. This is an optimization technique which creates an additional shard, so it doubles the number of possible connections, and it further benefits from absence of cookies. The assumption is you don't need authentication for the resources which are on the cookieless domain. How this sounds in HTTP2 world? Well, that second connection is potentially a good idea to kind of minimize that packet loss problem, right? Absence of cookies. If you are doing Hpack correctly, you don't have this problem. So should we do it or not? Yes, but in a very specific way. A web has a very nice mechanism for cookieless domains. Content delivery networks. Content delivery networks are generally great. They improve latency by being closer to the users, so the shorter path to travel, shorter time. Of course, in HTTP2 world, we want the content delivery network to support HTTP2 as well. This way we have only two connections, We put on the content delivery network all the big files, the third-party dependencies, images, everything that doesn't require authentication. We pay a small price for establishing the second connection. That price is further mitigated by the fact that these resources will download faster, so there is a return of investment. Content delivery networks are an evergreen optimization, regardless if you're on HTTP2 or HTTP1. And that kind of covers the invisible features of HTTP2, the ones that are triggered immediately after you switch. Of course, there is more to HTTP2. There are features which we as developers need to explicitly use. Server push. Server push is a completely new thing which came with HTTP2. It allows developer to push additional resources with the response. So the best way to understand a new feature is to experiment with it. And this is exactly what I did when I first encountered server push and wanted to understand it. I created a simple application, an index to critical resources. The technological background for this application is ASP.NET MVC, and my first attempt at server push was through HTML helper. For those of you who don't know ASP.NET MVC, which is perfectly fine, HTML helpers are something which runs during the rendering phase of your response, of your HTML. They have capability of outputting some HTML and doing other operations at the same time. So my HTML helper was grabbing a relative path, outputting it in a link or script element, performing the server push at the same time. This was the result. Do you see the difference? I don't. Yes, the times are a little bit different, but this is localhost, so that's negligible. So it doesn't work, right? Well, a lot of smart people have been designing this technology for a long time. And a lot of other smart people were implementing that in browsers. And I implemented that in my application, and I say it doesn't work. So probably I'm wrong. Probably it does work. So what you do in Chrome, because this was actually Chrome, when you don't understand how something works, you go to the internals tab. It contains a lot of information about what is going on under the hood. And it has a nice section for HTTP2. So I take a look there, and what I notice is that the pushed resources, the streams for them, has a lot lower priority than my response. That makes sense. Response is kinda important, so I guess browser wants to get it fast. So what was happening in the end? The push resources were waiting till the entire response downloads. Okay, let's try to do it differently. I moved my implementation from HTML helper to action filter. Now again, for those of you who don't know ASP.NET MVC, action filters are something which runs just after routing, before the business logic, generally, before the action. Action performs business logic, returns response. Action filter runs prior to this. So I was statically mapping pushes to my responses. And that was the result. Now I can see the difference. The times are really small. The chart looks different. There is something happening very early. That's the moment the browser receives the push. It parses the data later when it knows that it truly needs them, but they are already there. So that was the answer to the question I didn't even know about when I started to play with server push. The question is when to push, and the answer is as early as possible. Server push is designed to utilize server thinking time. So that time when network is actually doing nothing. Your server is processing, the network is free. This is a moment to push. It also tells you what to push. You want to push resources which are small enough to finish downloading before the actual response. The general rule of thumb, you don't want your push resources to compete with the response. For example, the stuff that you would inline in HTTP1, some critical CSS, some critical JavaScript, we sometimes inline that. That's perfect stuff to be pushed in HTTP2. Of course, this is not perfect. There is issue in this mechanism. There is something we're not utilizing here. Client-side caching. The oldest rule that the fastest request is the request not made is still valid. Actually, in cloud days, the request not made is the cheapest request. You don't pay for the transfer. So you want to utilize client-side cache whenever possible. Here, this is not happening. You are blindly pushing your resources every time. Browsers do attempt to support client-side caching here. There's actually a dedicated part of cache called push cache. It's not fully specified, it's browser specific, but every browser has it. And browser will try to help you. If it noticed you are pushing something it already has, it will cancel the push. But if your push is designed correctly, so it is very small, it will probably not do that in time, you will lose the bandwidth, you will lose the money. Luckily, this is actively being solved. There is specification in Works called Cache Digest. And the idea is very simple. Browser knows what's in its cache. So it can build an information, a digest, that server can later use to decide what to push. The digest is actually a well-compressed Bloom filter. You may know what Bloom filter is if you are working with low-level database stuff. You are probably not. The way you can think about it is, it's a set. It's a set which is optimized to answer a single question. Do I contain something? And there is a lot of discussion in that specification, which Bloom filter algorithm to use, should browser be allowed to modify the digest, should they recalculate it every time? So there will be some time before the specification will be finalized. But I wouldn't be showing you this if you wouldn't be capable of performing cache-aware server push right now. It's doable, thanks to service workers. Now you have probably heard about service workers. They are one of the pillars of the progressive web applications. The part we cared here about is that they are proxies. From general technical perspective, they are proxies. They are there in your browser between the client-side part of your application, the browser and the network. Every request your client-side part of the application makes goes through service worker. And service worker has cache API. They can manage the cache, they can inspect the cache, they can build the digest, then can attach the digest to every outgoing request in the form of a header. And there is a couple of ready-to-use service workers that do that. You can go to GitHub, GitLab, download it. What remains is your server-side implementation to actually inspect it. If for some reason you cannot use service workers, there is an alternative approach. You can try to use cookies. Then the whole burden is on the server. It needs to build the cookie, later inspect the cookie. And the challenge is in synchronizing the cookie expiration with client-side cache invalidation. And that's a very hard thing to do. And if you do it wrong, you will either end up over-pushing or you will end up with cache misses. Both scenarios, expensive. So the service worker approach is the preferred one. If you want to try to implement one of those, the link at the bottom, it describes how to attempt both implementations. So now we know how to properly optimize for HTTP2. A well-thought spriting strategy. A well-thought bundling strategy. No sharding. Content delivery network. Server push for critical resources, preferable instead of inlining. So all of those optimizations, except for content delivery network, they are bad for HTTP1 users. If you change that for what you have currently, their experience will degrade. How to deal with that? how to be responsible regarding them? The answer is protocol-based content delivery. Every decent server-side technology which claims to support HTTP2 should provide you with information what is the protocol of current request. Node.js can do that. ASP.NET Core, which has only experimental support for HTTP2, can do that. PHP can do that. So there is no excuse for a server-side framework to not be able to do that. Of course, this is not perfect. What's the issue here? Those of you who are more familiar with broader web architecture, how the web is actually built, they know that this kind of APIs, they work correctly if user is directly hitting your server-side application. That's not always the truth. There are not invisible intermediaries in our networks. Reverse proxies. And reverse proxies can be either local to your infrastructure, for example, Nginx or IIS, or they can be global like Cloudflare. Yes, Cloudflare is a content delivery network by name, but the way it works makes it a reverse proxy. So how reverse proxies deal with HTTP2? Of course they have to support it, but they support it only on the client to proxy connection. The connection from proxy to the server is usually HTTP1. So unless the proxy has some kind of the API, some kind of header, different mechanism that will deliver you the information what was the underlying protocol of the original request, you are blind. The only solution you are left with is to balance. Build a lab and carefully measure. Go as far into HTTP2 direction as you can without hurting HTTP1 users too far. That's very hard. And you can't use server push. It's HTTP1 connection. Well, proxies try to support server push. They will look for link headers indicating preloads, and based on them, they will push. But we already know, it's late. If you push headers early from the server side, you might help that, but you not always can push headers early. And it's still not perfect, it's still not good. So, in general, reverse proxies make it hard to fine-tune for HTTP2, fine-tune for both worlds. That said, if you are stuck with server-side technology that doesn't support HTTP2, and you know that majority of your users can benefit from that, then you can use a reverse proxy, even add it especially for that purpose, optimize for HTTP2. That might be the shortest path to give your users some benefit of HTTP2. And that's the entire picture of HTTP2 in the current network. This is how we use it, this is how we optimize for it. And there are still issues. There are still unsolved issues. So, what you are probably expecting that those issues are being actively worked on. And that's true. So, for a moment, I want to leave what we can do, and I want to move for what we can wait for to be done for us. There are two specifications currently in work, which goal is to further improve web applications performance. The first specification is early hands. Early hands introduce a new status code, 113, and they allow that status code to be sent earlier as kind of preliminary response. If you would telnet to a server which supports early hands, you would first get a normal HTTP response with a status code 113 containing some link preload headers, and then you would get the actual response after some time, after server thinking time. Now the goal is to solve the performance problems, the issues with server push. This will deal with the reverse proxy issue. The 113 response will simply go through the reverse proxy. This will deal with caching issue. It's the browser who is issuing requests for those resources you have indicated in your link headers. So the browser knows when it's cached, it knows what to request or not to request. The added value on top of server push is that you can use content delivery networks here. In server push, you have to push from your server, you have to utilize your own bandwidth. Here, you can point to any URL on the web. So you can point to content delivery network, the browser will download from there. This specification is actually approved as experimental. Implementation is a very big problem. That core assumption of web, single request, single response. It's deeply embedded in many implementations, in browsers, in intermediaries, in reverse proxies. It requires a lot of effort to change it. So there might be a lot of time needed before we see that in wild, if we ever do. That's not true for the second specification which is currently in works. Quick. Quick is a proposal from Google to solve that packet loss problem. It changes the transport. It's no longer TCP/IP, it's UDP, datagrams. UDP connections are resilient to packet loss. They don't care from the protocol perspective. Packet lost, whatever. Keep going. The hard part of this is that we actually need those packets again, and we need some ordering, and we need some resilience in HTTP. So the quick specification needs to redesign all those mechanisms that are lost after switching from TCP/IP. And the initial proposal from Google, gquick, actually does it fairly well already. But there is a proper standardization body which is working on actual official specification of quick. And the cool thing is that you can play with both of them already. The gquick version, it's there in Opera and Chrome. You can go enable it. There is a bunch of Google servers which actually speak it. So if you don't hit infrastructure issues, so again, HTTPS only, you can fire up Wireshark, observe how it works. You can also play with the latest version of the official standard. Cloudflare has, 2 days ago, announced that they have an experimental server that speaks the latest draft of the official quick specification. So you can play with that, observe how your application behaves, see how performance changes, and get the best possible. And hope that in future, your application will be extremely performant, it will be nice for your users, you will not lose money due to wasted bandwidth, due to long response time. This is my goodbye wish for you, for your applications to be as performant as possible. Thank you. If you have any questions, I got a couple minutes left, so you can ask them now. If you prefer, you can ask them later. I'm on the conference. You can reach me via Twitter. You can reach me via email. Thank you.